So based on what we have a number of underlying assumptions. And the first thing I want to do is the following. If we go back to this picture, you notice that each of these things, I can draw a little box around it. And if I draw a box around this one or this one, the neighborhood looks exactly the same. So that is what I'm going to call a cell. So the underlying assumption in our model is the fact that the fluid is made up of cells. And each cell has a single charged rod, which is our primary polymer. And it's surrounded by several small charges, in our case they're point charges, which have the same sign as the charged rod, but they're the secondary polymers. So our rod just consists of a simple rod with two charges at the ends, and then our little charges are point charges that are running around. And all of these interact with an AC electric field. Now we impose periodic boundary conditions, and what that means, going back to the picture that we had here, is that here's a cell and here's another cell, which means that if a particle goes out of this cell, it goes into the cell of the neighbor. So that's a bit like going out at one end and coming in the other end. And similarly, if it goes out the top, it goes into the neighborhood of another rod, which means that's a bit like, again, going out the top and coming in through the bottom. And that's what we mean by periodic boundary conditions. So we've got periodic boundary conditions, and that, as I said, just said that the secondary particles can move from one cell to the neighboring cell. Neighboring cell being up, down, right, or left. What's our motivation for doing this? There is this effect in physics called frustration. And frustration comes from the fact, and all of us have experienced it at different points of our lives, is the fact when lots of people want you to do lots of different things. What do? Well, if there are a few things, then you manage to multitask and take care of it. Well, if there are too many things, then you get frustrated because you can't complete many or most of the things. That's exactly what happens to these particles. If there are too many counterbalancing or countermanding influences, it can't really satisfy all of them. Or when I say it could either be the small particles or the big ones. If they can't fulfill all of them, then they actually do something weird, unusual. And that's what we'll see happens in this case. So that's our motivation to see if, in fact, this is a possible explanation for this anomalous orientation. There's a caveat here. Charged colloids in real suspensions are very, very complicated. Things move around with time. There are hydrodynamic effects that need to be taken into account. And to get taken together, they call electroosmotic effects. We're ignoring all of them. We're simply looking at it from an electrostatic perspective and asking ourselves the following question, which is that can a simple model which takes into account what are called collective plasma effects, meaning collective effects of lots of charges, is that sufficient to capture the essence of this anomalous orientation? So that's our motivation. OK. So now what are the variables? Well, we have a rod. And whenever you have a rod, it's a composite object, meaning it's made up of lots of particles. So you need to think about the center of mass. So we have to look at the position and the momentum. And by the way, the fact that they're in bold means they're vectors. So in our case, we're going to deal with a two-dimensional model. It could easily be three-dimensional. So we're going to do a two-dimensional. So it's a two-dimensional vector, position and momentum. And that denotes the center of mass of the bar. Each of the secondary particles, which each of the small point particles, has their own position and momentum. And there are n of them. We'll say what n is in a little bit. Then, of course, this rod needn't point straight up. It can tilt, which means we need an angle to describe the angle between the bar and the x-axis. And so the way we do that is through this angle, which we call theta. And also, based on that angle, we can specify the two ends of the rod, which are R1 and R2. And R1 and R2 are related to the center of mass position through the simple relationship. So this corresponds to a rod which has a length of 2L. You've got a mass and a charge on each of the small particles, which is m and q. The bar itself has two masses, which are m over 2, and they have two charges, one at each end. You've got the amplitude of the field. You've got the frequency of the forcing field. And just to make life easy, we make everything dimensionless, meaning we don't have to worry about whether it's in centimeters or meters or whatever, by measuring space in terms of the length, half the length of the bar, masses in terms of the mass of the small object, charges in terms of the charge on the small object, and time in terms of the inverse of the frequency that we impose. So what this allows us to do is it allows us to write the Hamiltonian, or the energy of the whole system, like this. And it has contributions that we can now walk through. So this is the kinetic energy of the center of mass of the bar. This is the rotational kinetic energy of the bar. This is the kinetic energy of each of the individual small particles. This is the electrostatic interaction between two small particles. This is the electrostatic interaction between one of the small particles and one of the charges on the rod. It depends on which end it is. So depending on which end, it either uses Q1 or Q2. And then finally, this is the interaction of the small particles and the rod with the external electric field. And you notice there's a J in front of the external electric field, and the J just means that it's pointing in the y direction. So as far as our orientation is concerned, when we say vertical, that's the same direction as the electric field. So this is the Hamiltonian. From the Hamiltonian, we can derive Newton's equations. And you've heard throughout the course, ultimately molecular dynamics is about the solution of a set of Newton's equations. And here they are. And so this one is the equation for the second order differential equation for the rod, center of mass. This is for each of the particles. And you can see that xi means that there are n of these equations. And then this is the equation for the rotational part. And over here, these quantities q tilde and n, etc., are all in terms of the scale that we talked about, which is the mass of the little particles and the charge on the little particles. There are two parameters that we're left with. And the two parameters are this, and which is the coupling, which tells you something about the coupling between the two small particles, and this, which is some dimensionless measure of the field strength. So it doesn't just say the absolute field strength outside is so many volts per centimeter. It puts it into perspective of some internal. Now, this life becomes much easier if we do what we do in physics quite often, which is to set the mass and the charge and the length all equal to 1. And if we do that, then it turns out that this just goes as 1 over the frequency of the electric field square, and the field goes as the field divided by the frequency square. So this is like a dimensionless length, if you like. In the simulations that I'm going to show you in all the results, the number of small particles I've taken is 50, unless I specify otherwise. Also, if you remember, when we go back to the Hamiltonian, you have this Coulombic interaction, which basically means that when those two distances get very small, it gets very large. And very large numbers make the differential equations much harder to solve. And so one of the things we do is we use a trick. It's called softening the Coulomb singularity, which basically means that when you get too close, you actually flatten out the potential, which means it can grow stronger, but it can't grow stronger beyond a certain point. This actually turns out to be not very significant, and there are real-world reasons for actually softening the singularity. We can make things more complicated if we want. We could add friction. We could make charges at the ends of the rod change with time. And we could introduce screening effects, meaning that if there's a charge sitting between me and you, then I'm going to feel less of an influence. So that's called screening, and we can put those in. But at the end of the day, ultimately, there are only two free parameters that I can change. One is the frequency of the external field. The other one is the strength of the external field. So what does this give us? It gives us this. So what is plotted here, this actually contains an enormous amount of information, because as you can see, this is log to the base 2 of the electric field. So this is about 3 or 4 orders of magnitude in terms of the variation in the electric field. And it's, again, about 2 orders of magnitude in this direction in terms of the variation of the frequency. And what is plotted here is the angle of the orientation of the rod with respect to pi over 2, which means 1 corresponds to an angle of pi over 2. Don't forget, the angle is measured from the horizontal. Pi over 2 basically means that it's pointing up in the y direction, which means it's in the same direction as the electric field. So that means whenever you see red, it means it's the normal orientation. And wherever you see blue, the angle is 0, which means it's the odd orientation. So that means if I draw a line going across here, what I'm doing is I'm fixing the strength of the electric field, but I'm varying the frequency. And one of the things you see is that for a range of frequency, you see horizontal, which is the anomalous orientation. And for another range of frequencies, you see vertical, which is the normal orientation. So you're actually moving from anomalous orientation or the funny orientation to the normal orientation through something which we will, in the paper we argue, resembles a phase transition. Over here, the green corresponds to a random orientation. So at very low frequencies, it's what happens is an odd particle comes close by and gives it a little kick, and the rod moves around and settles in at some angle. And if you do some, as a function of time, that angle varies randomly, and when you average it, you get an average value of pi/4, which is what you're seeing. So you get this very funny effect. And so if I plot this, which is what is drawn here, this line, as you can see, this is in units of pi/2. This is pi/4, so it's random here. It becomes horizontal, and then it becomes vertical, and then it goes to essentially the initial, this dotted line tells you what the initial orientation of the rod is. So in the high frequency, it doesn't move. So once you get to the high frequency, the rod is, the field is changing too fast for the rod to respond, and it just stays in the orientation that you put it in initially. So this is a curve that we can completely understand. Now the funny thing is, we can do something else. Here what is plotted is we started off with some value, and this is what the angle of the orientation of the rod does with time. And this time is measured in cycles of the electric field. So this is 20 cycles of the electric field. Similarly, this is another one which starts off at a different orientation, but you notice this one goes to pi/2, this one goes to 0. So pi/2, don't forget, is the normal orientation. So when we look, so here's the rod. The rod is somewhere in the middle here, and this is our cell. The rod is in the middle. It's pointing in the normal orientation. But you notice that the little particles are distributed all around the outside with a large concentration at the ends, at the corners. So this is very different from this situation where you notice that the little particles, this is plotting the concentration of the little particles, and the bulk of the concentration is above and below the rod. So you notice that depending on whether it's the normal orientation or the anomalous orientation, the distribution of the small particles is fundamentally different in the two cases. In the normal orientation, they're in the corners, whereas in the anomalous orientation, they stack up above and below. And the funny thing is that if you go back to that picture that I took from the experimental paper, this is the anomalous orientation, and notice that the way they asked the artist to draw this picture is to stack these particles above and below. And here they're much more evenly distributed around. And so they did have an idea for what might be the cause of this effect, and they were guessing that this would be one of the implications. And we found this in our molecular dynamics simulation. So what are our conclusions? So the first thing is that the distribution of those particles is strikingly different. The normal, they lie at the corners and the periphery. The anomalous, meaning the odd orientation, they occupy a much larger fraction of each cell, and that they're clustered closer to the primary particle. And the random orientation is most likely dominated by single events, meaning one particle getting a little too close for comfort, which nudges things. The other thing which is sort of interesting in our model, which the experiment doesn't have, is the fact that we have this cell. As you can see here, the cell is 3 units in this direction and 5 units in this direction. So the ratio of the x to y is 3:5. Now, of course, the normal orientation is this way, meaning the rod is supposed to be longer, the rod itself is longer in this direction than in that direction. So how does that affect things? So in order to, we asked this question, and in order to check it out, we frame the question in the following way. How does the phase diagram get affected by the aspect ratio? The aspect ratio is just the ratio of the length to the height of the box. And here there are two diagrams. The top one is the one you saw a few minutes ago. It has the random, it has the horizontal, it has the vertical. And this is, the ratio is 3:5, just like I showed you. So the x is 3, the y is 5. This is a square box, 4, 4. And notice what happens. The anomalous part is gone. So now you only have the random and the normal orientation. You don't have the anomalous orientation anymore. In fact, take a look at a few more results. This is the 3:5. This is the 4:4 with 50 particles. This is the 5:3. So here what I've done is, you would think there's no difference between 3,5 and 5,3. There is. And the reason is because the electric field is pointing in the y direction. And so now the short side is along the y direction rather than along the x direction. I mean, the short side is along the y direction rather than the x direction that we had before. That's right, got it right. But that makes a difference. If you switch to a 3,7, which makes it even longer along the y direction, then you get the anomalous phase back again. If you switch to the 3,5 but reduce the number of particles, 50 particles, 30 particles, 10 particles, 2 particles. So there are very few particles, it vanishes again. So you need some minimum concentration of the small particles in order to see this anomalous effect. But this clearly points to the fact that the small particles are responsible for this effect. So it again verifies what the experiment was speculating. And then finally, this is 50 particles with it doesn't necessarily have to be a ratio. This particular area is also interesting, and I'm not going to get into that here today. So what are our conclusions? Well, the conclusions are, the first and foremost, that the anomalous effect is clearly driven by the small particles, the secondary particles. There's a minimum concentration necessary for this to occur, and they have to be able to aggregate above and below the rod in order to allow for the anomalous orientation. And the reasoning is really, this is why the 3,5 works rather than the 5,3. Because in the 5,3 there isn't enough headroom for these small particles to accumulate above and below the rod. In fact, there isn't enough headroom for the rod to stand up straight. So the competing influences of the electrostatic potentials that act between the small particles and the rod and amongst themselves with the electric field, and the frustration that comes about from that, is what leads to this effect, because it's trying to satisfy all these electrostatic impulses. They're all forces acting on it, each one's trying to push it in a different direction, and the net result is it does something which is a compromise, and the compromise need not be the most energetically favorable one. And this is the idea that we're now trying to explore, that there is the picture that one sees when you change the frequency and the field strength of the electric field looks very close to a phase diagram that shows up in all sorts of physics and condensed matter physics, and this is something we'd like to explore some more. And finally, from the standpoint of molecular dynamics, you could do a much more complicated or complex molecular dynamic model where we could include the hydrodynamic effects as well, and not just the electrostatics. In which case, yes, it would be a lot more complicated. Yes, there'd be more equations to solve, but it'd be much closer to the effects that are seen in real colloidal suspensions. Much of what I've said here and more is contained in this reference, which is a paper that I wrote with a colleague of mine, Carlo Lancialotti, as published in the journal Chaos in 2008. I hope this gives you a sense for where molecular dynamics and the ideas that you've encountered in this MOOC may prove useful. Thank you.